Hey, hello again. For this lesson, we're not going to be doing kind of the traditional thing. I actually have assigned this lesson as homework, and I'm just wondering, how far you guys get. If you want to follow along here, that's fine. Hopefully, this can help with kind of the quote unquote homework. Um, and the reason is, I am less concerned about you doing the basic old, like, seventh grader type math formulas that you're kind of expected to know anyway. And I'm just curious to see if you could actually derive essentially pi. We're going to do two derivations of pi and get a derivation for these two formulas. Um, and the two formulas here are the circumference and the area formulas. So um, the circumference of a circle is equal to, and I'll draw the circle over here. So here's my circle-ish. This section here we're going to call R as the radius. The circumference is equal to, you should know this, the diameter times pi, or 2 times R times pi. So 2 pi R. The other formula you need to know is the area. The area, this is probably a formula you just memorized in middle school or something like that, or even elementary school, and you just had to use it a bunch of times. We're actually going to figure out where this formula comes from and how we can get it using our amazing powers of everything we've done so far. The area is equal to pi times r squared, right? Pi r squared. These formulas we're not going to practice. Well, okay, we'll practice some, but you should just know these, right? These are very fundamental formulas for some pretty fundamental math. You should be able to manipulate the area, the circumference, the diameter, the radius on circles, and just be able to switch back and forth between them all. People say, oh, when am I going to ever use this stuff? These sorts of things you will use all the time. If you ever happen to work with anything circular, your tires on your car, you're like, oh, what is this? Like, everything with circles, you need to be able to do this, right? I don't care if you're baking cakes or whatever. Granted, yeah, you won't be doing like tons of formulas all the time, but these are just really fundamental things about the way the world works, right? The wheel was invented thousands and thousands of years ago. We just kind of need to know the basics of how it works. Okay, that being said, we're going to derive it. So, in the Explorer for 16.1, it says justifying the circumference formula. To find the circumference of a given circle, consider a regular polygon that is inscribed in the circle. So here's my polygon. As you increase the number of sides of the polygon, the perimeter of the polygon gets closer to the circumference of the circle. Right? So here's my 5-sided polygon, here's my 6-sided polygon, here's my 8-sided polygon. If I had 9 or 10 or 12 or 15 or 100 or 500 or 8,000 or 700 million, it would get closer and closer and closer and closer to a circle, right? That's the point. That's why we're doing this, is because we're going to get super close to a circle and we can basically calculate that circumference. So this is going to be our generic setup. A lot of people get thrown off by this picture because this picture has 6 sides, right? They used a hexagon. They have to use some shape, right? They can't just make an amorphous blob. So they picked the hexagon. However, the book here is going to want you to generalize for any polygon. That's why they have these dotted lines here, right? To just kind of indicate that you could fit any number of these types of lines in here and make it any number of sides. So if it helps to start by thinking of it as a hexagon and then kind of go back and be like, all right, when did I use the number 6? That's fine, but keep in mind here, we're going to try and find a general form for any polygon here, using n as the number of sides of that polygon. And we can find the perimeter of a polygon pretty easily, right? If I can find this length, right, let's say it's a hexagon. If I can find this length, I simply take this length, or this length, or this length, they're all equal, it's regular. and multiply it by the number of sides. So I take that length, multiply it by 6, I get my perimeter. So that's the general form we're going to use as well, is to calculate the perimeter of these. Stop it. These shapes. Okay. And then it says, let AB be one side of that n-gon. So AB is one side here. Draw OM, where we go from the midpoint down to the mid-segment of AB, right? Okay. Then it asks, how do we know that these two triangles are congruent? AOM, AOM, and BOM. Well, we know they're congruent because we know that the radius is congruent to the radius. We know that this line to the mid-segment is congruent to the line to the mid-segment. And we know that since this is the midpoint, this is congruent to this. Oops, put through there. So which triangle congruence theorem are we going to use? Angle, angle, or angle, angle, side, side, side. Side, 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 triangle congruence theorem, right? So we know these two triangles are congruent. Therefore, what's true about these two angles, angle 1 and angle 2? Well, those are also congruent. Corresponding parts of congruent triangles are congruent. And then finally, it asks here, if there are n triangles, all congruent, that surround point O and fill the n-gon, what is the angle AOB? So we look up here, we look at angle AOB, so A to O to B is this angle here, and they just want to know what this angle is. And a lot of people just say, oh, it's 60, because I take 360, I divide it by, I know there's going to be 6 of these in this hexagon, so therefore 360 divided by 6 is 60, which is true, but remember, we want a general form. We want an answer that can apply to a pentagon and a hexagon and an octagon and a decagon and everything else. So what would it be if it was an n-gon? Well, when we got 60, we took the whole, the 360, and divided it by 6, right? So in this case, 360 over 6. But if it's an n-gon, we're going to get rid of that 6 and just do 360 over n, right? Where n is the number of sides. Because that's how many of these little triangles we'll have and how many chunks we have to break up that whole circle into these little, those little angles. Okay, so that gives us 360 over n. And now it's asking for what is the measure of angle 1? Well, the measure of angle 1 is simply 1/2 of the measure of the big angle. Right? So there's the measure of angle 1. That's simply half of AOB. If this is AOB, what is half of AOB? Again, it's 30 in this picture only, but we want the general form. So what is 1/2 of this value? I'm going to let you guys think about that. Try not to think about, delicious Girl Scout cookies. Well, we can take half of that value, 180, also divide that by n, and this is 1/2 of the value. Okay, so 180 over n. Bear with me here for a second. Since this angle, OMA, is congruent to OMB, and OMA and OMB are a linear pair, that means they're 90 degrees, right? We kind of looked at this. So it's basically saying that, okay, this is a 90-degree angle, this is a 90-degree angle. So since this is a triangle, I'll draw one of these. Since that's a right triangle, let's say we want to find x, right? We want to say x equals what? And we can actually do that using some right triangle trigonometry. I'll back up here for a second. If we know what angle 1 is, and we know what the radius is, what would be our expression for x? Well, angle 1 is this angle here. This is the hypotenuse. This would be the opposite side, right? So we need an expression with opposite and hypotenuse. That's sine. So the sine of angle 1 here, angle 1, equals opposite over hypotenuse, or x over r, over r. Therefore, when I rearrange this, it gives me x equals r times the sine of angle 1. Okay. So x equals r times the sine of angle 1. That's where they got that value from. Here. Okay. We can go further than this, though. We know what angle 1 is. We have an expression for angle 1. You guys remember what that is? It's just right up here. Angle 1 is equal to 180 over n. So we can substitute in 180 over n for angle 1. And that gives us x equals r times the sine of 180 over n. So now we have an expression for x. And do you remember how we got the perimeter of this polygon using x? Well, we have x here, right? We have this is x. So this whole distance here is 2x. And then we multiply that 2x by n, right? Because n is the number of sides in the polygon. So we have 2x. So the perimeter of the n-gon is 2 times x times n. And then we can plug in our expression for x. So 2 times n times r times the sine of 180 over n. Cool. We're almost there. Now we can start to basically calculate pi. Yep, that worked. Okay. You could use a graphing calculator and start plugging in a whole bunch of numbers at once. I would like to just have you think about a single circle here. So go ahead and pull out a calculator. I'll call one up here in a sec. If we have a circle, and this time I'm going to make the radius r equals 0.5. The reason why I'm doing this is so the diameter is 1. When the diameter is 1, the circumference is pi. So this way, when we calculate the circumference, we're calculating pi, right? So let's go ahead and see if we can calculate what this value is. Now, we have n in here, and we're going to want to just pick a big number, right? The bigger the number, remember, the more sides in our polygon, the closer we'll get to pi. Other thing to notice is since r I've set at 0.5, I'm going to cancel out this 2 and this r for our purposes here. And we're simply going to deal with n times the sine of 180 over n. And then, again, we just want to pick a really big value. So let's think of a really big value. How about, say 900, and whatever, just 99. Let's see if 99 will get us close. 99 is pretty big. It's not huge, right? We got really big numbers. You can do, a couple million or a couple trillion, whatever you want. But the bigger the number, the closer you'll get. So for this case, I'll set this thing equal to n, and we'll plug n in here. So let me call up a calculator real quick. I like to just do 4 plus 4, and then just use the Google one that comes up here. Clear that out. So the number I picked was 99, so I'm going to pick 99. I'm going to take the sine of, go back to the formula. We're going to do n times the sine of 180 divided by n, right? So I'm going to go 99, that's a little better, times the sine of 180 divided by 99, right? Plug all this in. Let's see what we get. We get, wait, where did I mess up? Sine of 180 divided by, oh, look at this. Whenever you mess up on a graphing calculator, you know what it is, like 90% of the time? I was in radians. We're going to change to degrees. Okay, well, let's try that one again. 99 times the sine 180 divided by 99. And that gives us 3.14. Ta-da! The other digits are wrong. 3.14 should be 15 something. So it's not super accurate, right? But we only went up to 100. If we were to plug in a bigger number, I'm sure you'll get a more accurate answer, right? We can do 9999. That's at 5, 6, 7, 8, 9. We'll do 9 nines times sine 180 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9. Make sure those match. Equals 3.141592653. Goes on. It rounded a little bit, but yeah, that's perfectly accurate. Okay. So cool. We got that. Therefore, our value gets closer and closer to pi, which would be the circumference of that circle we set up earlier. Cool. We just proved the circumference formula, right? We could have plugged in other values for r and seen how they're related to pi and r and stuff, but we just picked 0.5. So 2 times 0.5 times pi is the perimeter. Okay. The other one we're going to do is the area formula. Again, we know the answer to this. We know that the area we're going to get at the end is equal to pi times r squared. But we're going to derive it. It's actually a little bit simpler in some ways. So we're going to do the same thing. We're going to get more and more polygons here. We have our setup AOB. We have X as right here. For this guy, though, we also have H. We need to care about the height of this triangle because the area of a triangle equals 1/2 base, in this case X, times height. So that's going to give us the area of this triangle, right? And in fact, the area of the two triangles would just be base times height. We can scratch that one off. So we'll explore that. So this one says there are n triangles, all congruent to triangle AOB that surround point O and fill the n-gon. Okay, we buy that. Therefore, the measure of angle AOB is 360 over n, and angle 1 is 180 over n. Same deal. Nothing's changed. We know that x equals r times the sine of 180 over n. Also, we just stole that from earlier. That's fine. So we want a similar expression for h. Okay, let's figure out h. Let me go back here. We're just going to focus on one of these triangles. I'll do the one on the left again. So this triangle here, we need an expression for h. And we could do h either as an expression of r or as an expression of x. Let's do it with r, just like we did before. So according to angle 1, right, relative to angle 1, remember this is a 90-degree angle here. This is the adjacent, and this is the hypotenuse. So I'm going to use cosine. So same deal as before. Cosine of angle 1 is equal to h over r, or I could say h equals r times cosine of angle 1. Remember, angle 1 is also 180 divided by n. We came up with that. So h equals r times the cosine of 180 divided by n. Okay, and then we come up with our area formula, 1/2 base times height. Remember, these ones cancel. Ba-doop-ba-doop. It just gives us x times h. Gives us the area of the big, not the blue triangle, but the big one here, the double triangle. So we know that x is r times the sine of 180 over n times h. And then we can just plug in our new value for h. So that gives us, they're going to skip a step here, which I'm not a big fan of, but that's okay. We have r times the sine of 180 over n times r times the cosine of 180 over n. So r is in there twice, right? We have two r's. We have r times the sine of 180 over n times the cosine of 180 over n. So that's where this value comes from. And that's where r squared comes from, right? We have r for the x value, and then we have an r for the h value. There are n of these triangles, so therefore, the area of that n-gon is simply this area times n. So we can multiply that whole shmear by n, and that gives me that big equation. This is going to be the one we're going to plug in with a big value again. So our expression for the area of the n-gon includes the factor as n gets larger and larger and larger, what happens to this? Again, we're removing the r squared because we know that the formula is pi r squared equals the area. So if we remove the r squared, we're going to be calculating for pi. So let's go ahead and plug this in right here to our calculator. Remember, it's n times the sine of 180 over n times the cosine of 180 over n, and we'll see what value we get there. We'll try just the 99 for starters again. Okay, 99, whoops. It was n times the sine of 180 divided by 99 times the cosine 180 divided by 99, right? Did I do that right? 3.14-ish. More sources of error because we put this small value in here twice. So, but 3.14, yeah, they're close. We can do a little bit better. 3, 4, 5, 6, 7, 8, 9 times the sine of 180 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9. This might not let me. It might be too big. Times the cosine of 180 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9 equals 3.14159265358. Yep. So it's perfectly accurate. Perfectly. Yeah. Awesome. So as we get closer and closer to infinity, that expression right here gets closer and closer to pi. So therefore, the area gets closer and closer to pi r squared. Cool. So we just derived both of those formulas. This isn't something that you need to know for testing. However, it is something that I think is interesting and does help you in the long run for understanding how the world works and where in the world they get pi from. We basically calculated pi in two different ways, was to calculate that value, and we calculated both these formulas. So props on you. We'll see you next time. Thanks.